So, Learning Unit 4 is all about making solutions. So, since we've talked about it in class, I thought I'd summarize the three short pieces we had at the beginning of every class to talk about qualitative aspects of solution formation, quantitative aspects of determining solution concentrations, and then putting those two pieces together. When we form solutions of solute and solvent, how can that affect the properties of the solvent, like boiling point, melting point, and vapor pressure? And that's what we call colligative properties. So the first video here is just to sort of talk about the qualitative aspects of forming solutions. So some D and S words that are going to become important to our vocabulary as we move forward in this learning unit. We're going to be talking about solutes being dissolved or dissociated in solvents to make solutions. Now, we'll get more into the quantitative piece in just a little bit, but in general, solutes are in smaller concentration than solvent. Solutes can actually be solids, liquids, or gases, but when we mix these together and form solutions, we can think about the energetics of this process in a couple of ways. So a few other pieces just to highlight here, defining some different types of solutes that we can have. In general, we're going to have solutes that are ionic compounds and then solutes that are covalent compounds. Ionic compounds are what we call electrolytes, meaning that not only do they dissolve, but as ionic compounds, they dissociate into ions. Okay, we call again those electrolytes. A great example would be table salt as sodium chloride. A solute that is a covalent compound that dissolves but does not dissociate is something like table sugar, which is sucrose. And if you look at its molecular formula, you'll see that that's something that is not going to break apart into ions in solution, and we call that a non-electrolyte. So very simply, and we're going to see this throughout this learning unit, solute plus solvent gives us a solution. So at its core, what holds solute particles together are intermolecular forces. What holds solvent particles together are intermolecular forces. And when we mix solute and solvent, at its core, what we're asking is a disruption of solute-solute interactions, a disruption of solvent-solvent interactions, and then in that new solution, new intermolecular forces. And at its core, if we know a solution process happens, our costs must outweigh our gains. I'm going to flip through a couple of slides really quickly here because they're things that we've talked about already, but this is leading into a theme for chemical energetics. When we talk about chemical processes happening, in general, chemistry likes to happen to go downhill, which means the costs of our chemical process must be compensated for by the gains in other processes that happen. So we talked about that with our bank account. Again, flipping through these slides quickly. If you need to go back for a review on this, I believe it was Learning Unit 2 when we talked about sort of the energetics of chemical processes. So we introduced it sort of as a bank account analogy. We expanded on it when we talked about ionic compounds and lattice energy, and then we built on that further with covalent compounds and bond energy. So those are some really busy slides, but again, highlighting that chemistry happens specifically with an enthalpy sort of component for us to think about the contributing costs and gains to end up with a net sort of overall enthalpy for the process. So we can think about the same thing for solution chemistry. When we form a solution, we are asking the solvent intermolecular forces to be disaggregated or broken, the solute intermolecular forces to be disaggregated or broken, and then when we form a solution, we have new intermolecular forces. And if these two costs are more than compensated by the gains of the new intermolecular forces that are formed, then the overall process is going to have a negative delta H. It will be an exothermic process, right? Energy goes downhill. An endothermic process basically has the disaggregation enthalpies, those costs, being something that is not compensated for by new intermolecular forces that we get when we form our solution. Now, it's not to say that endothermic processes never happen. We've yet to really dive deeply into a second component of chemical energetics, which is entropy. So I'll put a pin in that for now. We'll revisit entropy later, but you can have endothermic processes that are overall spontaneous or favorable because we have entropy that's contributing. And again, we haven't fully studied entropy yet, but we'll get to that later. So that's just a brief introduction to the qualitative aspects of forming solutions by solute and solvent interacting.